me, it's a slogan for now. I'll try to hopefully make it precise. What I'm trying to suggest to all these examples is look at the function that you are assuming is Morse like. It's not Morse. To choose a critical point, well, by constructing all these examples, the critical set is not an arbitrary set. It's a disjoint union of submanifolds. So choose a connected submanifold. Choose a point P here. So look at the original Hessian. The original Hessian will turn out to have lots of zero, like null spaces, simply because F will turn out to be constant on the component. So you cannot ask for the Hessian component along the directions of N, but in the directions normal, you want that restricted Hessian to be. So again, if you go back here, if you are at a point here, if you are moving along this direction, the Hessian is 0 because the function is 0. But if you move in the normal direction, so you'll be either flowing down this way or flowing down this way. So you're actually moving. So the Hessian is non-linear in that direction, but there's only one normal direction because this subsumes dimension 1 and the ambient dimension is 2. That is what you want to capture, and then you expect a similar Morse lemma for such functions. Right? You have a coordinate system where it looks like summation negative squares, summation positive squares, but the total index is going to be n minus the dimension of this thing where you're analyzing. Because along that submanifold is okay. So I mean that's the setup. It's still a bit vague perhaps for some of them. But are there any questions, comments? Everybody making sense? Okay. Yeah. So yeah, so this one, unfortunately or fortunately, we don't go by what Morse. You can, but it's just Morse and then Morse. So you might want to put it alphabetically, but I just got it. So if the critical set yeah, so that's the first assumption, that it's a disjoint union of submanifolds. So here, for instance, if you literally want to look at the connected components, there are 3 components. I'm writing it as 4, but this is really 2 disjoint points. So you look at each component and then you want to analyze what F looks like along that component. So you realize that Morse functions are special cases because for Morse functions, critical set is a disjoint union of submanifolds of dimension 0. So that's why it had all those submanifolds and for connected component. Look at H. This is by definition. Well, there are several equivalent ways to say this. One is that you want the Hessian to vanish around P2 for every P, and on the complementary thing, you want it to be non-linear. Yes? This one. Yeah, so I'm saying this is a disjoint union of submanifolds. Like here, this is a disjoint union of 3 submanifolds. That's 1 point 1. Choose one connected component. That's a connected submanifold in the critical set. Right? Now for that choice, and look at a P in here because every P is here, so which means every P lives in exactly a unique connected component. So I look at this thing, which is the restriction of F. Let's do this here. So I think I'm writing it not the most efficient manner, but ideally you could assume that. So what this is a digital network submanifold, and the Hessian vanishes along EPA, so along the tangent directions in the in the critical submanifold any itself, the Hessian is. So it makes sense to look at the restricted Hessian on the complement. This TPM simply means it's the orthogonal complement of TPM inside TPM. So then is a submanifold N. This is happening in TPM. The Hessian was defined on TPM. So if you ask, okay, what is the orthogonal
TPM? TPM plus entire tangent space.
Yeah. So I want this to be non-linear and it should vanish on TPM.
No, probably a bit more than TPM. It is on bilinear.
Yeah. So if you put anything in TPM or anything in the other slot,
anything other slot.
Yeah.
So TPM.
Yeah. Okay. So you want to, I guess, I could have said you want TPM mod. So there's an induced map from TPM mod TPM across TPM mod TPM to this. Yeah. So if you put the Hessian, if you put anything from the tangent space and anything in the other slot, that's it. And so hence, it's like saying you have a map from B cross B, which is TPM cross TPM to R. And in any slot, if you put from the subspace W, which is TPM, this bilinear form vanishes. So it induces a map from B mod W cross B mod W to R. But if you are used to Riemannian metrics, then you could choose a metric on N, whatever that is, and then identify B mod W with W mod. That's just a convenient choice. Hence I'm writing this, but this requires a choice of a metric. So if you don't want that, simply imagine this to be a induced bilinear form on TPM mod TPM cross TPM mod TPM to R. So in particular this is implicitly assuming that this thing vanishes in one of the variables is TPM. So there's an induced map from the quotient, or if you are used to Riemannian metrics, there's an induced map to the orthogonal form. This requires a choice. It's the usual thing. You go from B mod W to W for irregular form. So yeah, so I just finished it for my component. This yeah, I could have written this first. Yeah. So in any slot, for the symmetric, it doesn't matter which slot you put, anything in the tangent space, this form vanishes. Which means there's an induced map from TPM mod TPM, because TPM is subspace of TPM. And so if you want, you can interpret this as saying HM. We don't like metrics as a map from TPM. This map is a non-linear symmetry. So, if you go back to this example, there is only one normal direction here, right? And it is actually flowing down in that. Similarly here, the normal direction are, and it is non-linear in that normal direction. But here, of course, you have, like the normal direction, there's 4-dimensional Wattson direction, so there is extremes. But this is not a generic example, this is true. Whenever you have a fiber, single fiber problem, you choose a Morse function on the base, you have a Morse spot function on the base. So the critical set is going to be a whole bunch of copies of the fiber. So critical set is not varying in dimensions, but you still have to use the map pi and the map p2 here to see what's going on. Yes. Yeah. So I should have said this. Okay, so this that for a connected top. Yeah. So this is so that induces a map like this.